Okay, it looks like we're live. Um, so hello everyone, welcome to our online quantum chaos seminars. Thank you again for joining us. Um, as usual, today we'll have a seminar in which you can look and watch on the YouTube live stream, and you can ask questions through the live chat. And we encourage you to do that throughout the talk and at the end as well. Um, Today, it's our pleasure to introduce our speaker, Bin Yan from Los Alamos National Laboratory. Bin got his PhD from Purdue University, and in the summer of 2019, he started a postdoc at Los Alamos. He had actually already been working with Wojciech Surek during his PhD. Bin's research interests include quantum information, statistical physics, and fundamental physics in quantum logic and probability, among other topics. And today he'll be telling us about the quantum zoo of butterflies. So thank you, Bin, once again, and you can take it away whenever you want.
Okay, thank you, Pablo, for the kind introduction and the great opportunity for giving a talk here. Today, I'll be sharing some of our recent works in the topic of quantum chaos and the butterfly effect. Yeah, I'll first give a brief introduction to the problem, classical and quantum chaos in the time domain, the butterfly effect, and then I'll introduce three types of quantum butterflies: the Bradbury butterfly, Lorentz butterfly, and anti-butterfly, related to different types of measures for quantum chaos. And those terms will become clear towards the end of this talk. I'm very happy to answer any questions during the talk. So if you have any, please feel free to stop me and type in your question in the chat section. Okay, so the field of classical chaos is well developed, and it is well known that classical chaotic dynamics is extremely sensitive to initial conditions. And this is also known as the butterfly effect. And the term butterfly effect is well known and even publicly known, mostly because of Lorentz famous words about the flap or butterfly's wing. It's a very fantastic description of this effect. But I think what is less known, and I think this is where some of the credits should go to, is the Bradbury story about the butterfly effect. In the year 1955, Bradbury wrote a science fiction, A Sound of Thunder, where he described a person using a time machine traveled back to the deep past to hunt some dinosaurs, but accidentally killed a butterfly. But when he traveled back to the present, he noticed a totally different world. And this is another description of the butterfly effect. So in comparison, in the Lorentz story, we actually start from two slightly different initial states and compare those two time evolutions. But in the Bradbury story, we actually start from one initial state, go back in time, and then apply perturbation, travel back to the present, and then compare the final output states with the initial state. So, and you may have already realized that those two stories are equivalent, at least in classical physics, because you can interpret Bradbury's story as the Lorentz version by thinking of these two slightly initial states from the past. And those are indeed equivalent in classical physics, but I'll show you in a moment that there is a subtle difference in quantum mechanics. And those ideas about the butterfly effect have been formally developed in the whole framework of classical chaos. Roughly speaking, in a classical phase space, nearby trajectories diverge exponentially fast, and with the exponent known as the Lyapunov exponent. And of course, if we have a n-dimensional phase space, we can apply perturbation along n possible directions and compute the divergence in distance along another n directions as well. So in essence, we get a n by n matrix. This is known as the Jacobian matrix that quantifies the instability of the phase space. And if we diagonalize the matrix, we get a full spectrum of Lyapunov exponents instead of a single one. This is known the Lyapunov spectrum. I will come back to this point with the quantum version of the Lyapunov spectrum in a moment. The situation in quantum mechanics is much more subtle. The first naive conclusion we can get is that there is no butterfly effect at all, because Schrodinger equation is linear. And we know that linear dynamics is not sensitive to initial conditions at all. To make the statement more formal, think again the Lorentz version of the butterfly effect. We start from two different, slightly different state here. I use P and P dagger to denote the perturbation. In general, a generic perturbation may not take this form, but since we know that a generic quantum channel, a quantum process can always be written in a sum of different terms like this. So this is really the building block of the process. So I'll restrict myself to this type of perturbation. And then we can keep track of two time evolutions. If we take the overlap between those two time evolved wave function, we get a constant. And we get a constant because the evolution is unitary, and unitary preserves the angles, preserves the inner product. And I like to emphasize that the inner product is really not a measure of distance, because distance should be non-negative. And by overlap, I really mean that a distance measure based on the overlap, based on inner product. And because the inner product that doesn't change, so any distance measure based on inner product will not change. So in this sense, we can conclude that there's no butterfly effect at all in quantum mechanics. On the other hand, it is well known that quantum systems with chaotic and non-chaotic classical limits or classical counterparts show different characteristics in the energy domain. And for example, if you compute the correlation functions of the energy spectrum, you may get different signatures for chaotic and non-chaotic systems. So we do have a field for quantum chaos, and at the early stage of the study for quantum chaos, the focus is really on the energy domain. And this is the reason some people like Barry suggest that we should call it quantum chaology, not quantum chaos, because it's not in the same sense as the butterfly effect in classical physics. However, there are certain attempts that try to tackle this problem in the time domain as well. The first attempt, maybe not the first one, but I would say it's fair to say it's the first well-known and well-developed one, is a quantity called the locksmith echo, introduced by Asher Paris almost 20 years ago. This quantity computes the overlap between two evolution from the same initial state, but with two slightly different Hamiltonian. So in essence, we apply the perturbation not to its initial states, but to the Hamiltonian. And the overlap indeed decays very fast for chaotic dynamics. But of course, there are other subtle issues related to the locksmith echo. And even for integral systems, we also get decaying behavior for the locksmith echo. And the distinction between chaotic and non-chaotic only shows up clearly at the early stage. But nevertheless, this quantity indeed captures some type of sensitivity of chaotic dynamics, even though not precisely an analog to the classical case. More recently, there's another quantity named the out-of-time autocorrelator, which has attracted a lot of attention across different fields in physics. And it is formally defined as a 4-point correlator with unusual time ordering. Now A and B are usually chosen as local operators on different subsystems, and AT is the Heisenberg evolution. The average is taken over a given state, but it can be generalized to average over a thermal state or any other states. And this quantity decays very fast for chaotic dynamics as well. And there are many different perspectives for interpretation of this quantity. For example, the operator growth perspective, because A and B are initially local operators on different subsystems, they initially commute. But due to the Hessenberg evolution, the evolved operator A of T would become a global operator over the entire system. So it starts to non-commute with operator B. And this non-commutivity caused the decay of the OTOC. And how fast the OTOC decays actually indicate how fast the operator A of T spread over the entire system. And people from quantum information may argue that, well, this quantity precisely captures how random the unitary operator is, because it's a fourth order correlator, actually a detector for unitary tool design. And more recently, we have successfully built a connection between the OTOC and with the old-fashioned quantity loss-meter echo. And under some mild condition, you can identify an effective perturbation in the problem that relates the OTOC to loss-meter echo. I'm not gonna go into the details of those different perspectives, but I'll try to present another perspective, which I think that's very interesting, from the Bradbury's perspective of the butterfly effect. Again, take the Bradbury's setup. We start from the initial state rho, go back in time, and then apply perturbation, go forward in time. And then we compute the overlap between the initial state and the final output state. If we do the overlap, what we get is precisely the form of OTOC. Now we can switch to the Hessenberg picture and use the operator, the quantum state as the operator. So we have the freedom to choose any local operator, rho. We also have the freedom to choose any local perturbation P. We can also add some type of Wheatian in the trace, so we can get any type of OTOC. So the first point I'm trying to make here is that OTOC is actually the Bradbury butterfly. Right? Now we get the Bradbury butterfly. What about the Lorentz butterfly? I've shown you at the beginning that we don't have a Lorentz butterfly. But if you think of it harder, you notice that you realize that the issue is that we're using overlap as a measure to quantify the difference, the distance between two time evolution. And the overlap is not a very good measure. It's a global measure. It cannot detect the difference, the local difference, unlike the OTOC, unlike the OTOC case. So we need to come up with another distance measure. Our solution is to adopt a notion called the circuit complexity, initially motivated from quantum computing. So what is circuit complexity? Imagine that you're trying to simulate a given target unitary on a quantum computer, but you only have access to a given set of quantum gates. Those quantum gates are usually taken as local gates, single and 2-qubit gates. And of course, you have many ways to realize the simulation, to simulate the target unitary. The circuit complexity is then defined as the minimum number of gates you need to realize the simulation. It's a well-defined quantity. And then we can also adopt this notion of circuit complexity and define a complexity between any two given quantum states. This is defined as the minimum circuit complexity, which we have just defined, for any possible unitary that transfer one state to another. Okay, so we're involved into a double optimization. So we have to optimize all possible unitaries that connects those two target quantum states. We get a well-defined quantity, but it's not very friendly to work with because it's not continuous. Nielsen and collaborators took this idea and developed it into a very appealing framework for complexity. So the abstract setup is this. So we are given a set of operators or generators, and we are trying to build up an effective time evolution such that the evolution operator matches the given target unitary. And we have this freedom to choose all the time-dependent evolution. Of course, there are many ways to realize the simulation. And then we define a cost function that assigns a cost for each possible realizations of the simulation. And our task is to minimize the cost and define the minimal cost as the complexity for the given target unitary. And as before, we can adopt this notion and define a complexity between any two given wave function, the reference wave function and the target wave function. That is the minimum unitary cost with respect to all possible unitaries that transfer one state to another. Okay, and you can track that this quantity, the state complexity, the relative complexity between two states is non-negative. It is also symmetric, and it also satisfies the triangular inequality. So it indeed qualify the distance measure. So we can treat it as a distance. And this framework is appealing because the problem of computing the complexity is reduced to the problem of finding the minimum cost. Well, the minimum cost is given by the minimum length of the path in the manifold formed by the given operators, right? So the problem is actually reduced to the problem of finding the geodesic in that manifold. So all we have to do is to solve the geodesic equation. And in that manifold, the metric of that manifold is actually fixed by the cost function. Okay, to give you a feeling, let's take a very simple example. It's a single qubit on the Bloch sphere. So the manifold is just the Bloch sphere. Of course, if you can rotate the single qubit along any axis, the geodesic, it would just be the grid circle. But suppose that you only have access to rotations along x and y axis, but you cannot directly rotate along z. In this case, the geodesic connecting those two given boundary condition is the solid curve. It's no longer a grid circle. Okay. So now we have a well-defined framework for computing the distance, the complexity distance between any two given target wave function. We can use it and apply it to the problem of quantum chaos. Again, taking the Lorentz picture, so we start from two initial wave function. One is slightly perturbed, so we have two slightly different initial states, and we just keep track of two time evolution. We can compute the complexity distance between those two time evolved wave function and see what we get. And we are particularly interested in the classical limit because we wanted to say whether our framework can recover the whole set of classical chaos, the whole theory of classical chaos. So to do that, we choose our generators. We choose the given set of operators as a Heisenberg algebra. And the reason is that if a quantum system has a classical counterpart, you can always find a set of canonical variables corresponding to x and p in classical phase space. And those variables in quantum mechanics form a Heisenberg algebra. Okay, I'm not gonna go into all the technical details of the problem, but I'll just leave the most important takeaway message of this framework. And we do find that at the early stage, at early time, the complexity distance indeed grows exponentially fast, such that we can extract a single Lyapunov exponent. And again, like in the classical phase space, because the degree of freedom we have in the given set of operator is matches the degree freedom of the classical phase space. We have n operators. N is classical phase, the dimension of the classical phase space. We can choose our initial perturbations in n possible directions. And because the complexity is computed at the length of the geodesic, we can choose to compute the length with respect to a given direction. So basically,
Can I ask
we have
a quick question?
Yeah, sure.
So is there any assumption on your initial states, as in they are ground state or some low-lying states, or does this hold for generic states?
So our framework applies to any, you can choose any quantum states. You get any time evolution, you can compute the complexity distance between any state. There's no restriction at all. However, because we are interested in comparing the classical limit of our framework with classical chaos, we usually choose our initial state as a localized state in the phase space. Yeah.
Okay,
and
thanks.
by the early time, what I mean by early time is that the localized state in the phase space is still localized, such that the classical dynamics matches the quantum dynamics. That's the meaning of the early time.
Great, thanks a lot.
Yeah, so we have n possible directions for the initial perturbation. We can also compute n possible directions. So just like in the classical phase space, we get a n by n matrix in analog to the n by n Jacobi matrix in classical phase space. And if we diagonalize that, what we get is that the quantum version of the spectrum exactly matches the classical Lyapunov spectrum. Okay, so in that sense, the classical chaos is fully recovered in the classical limit. And moreover, all those results is independent of the choice for the cost function. This is very remarkable because we know that the classical Lyapunov spectrum is also independent of the metric for the phase space. Looks like we have a complete picture, a very good ending. So we have a Bradbury butterfly. We also have a Lorentz butterfly that corresponds to different measures of quantum chaos. Both the Lorentz butterfly and Bradbury butterfly also exist in the quantum world. Of course, because they are initially introduced in classical chaos, and they are generalized from classical chaos to quantum mechanics. But we also know that quantum mechanics is beyond classical physics, in the sense that there are many effects in quantum mechanics that do not exist in quantum physics. So the next question I'd like to ask is that if there is a type of quantum butterfly effect that exists only in quantum but not in classical physics, the answer is yes. In a recent work, we studied this simple problem. This is basically a Bradbury process. So Alex can prepare an initial state and let it pass through a backward evolution, apply a perturbation, and then let it pass through a forward evolution. Okay. So in our setup, the perturbation is given by random projective measurements on Alex qubits. It's a very special type of perturbation, and it's not small at all, because if you do random projective measurements on Alex qubit, you actually destroy all the information on that qubit. You also destroy all quantum correlations between Alex qubit and the rest of the system. And don't worry about those quantum gates. The single quantum gate P is just used to prepare Alex initial qubit. Those the R and S and the C naught here are used to effectively realize the perturbation. No, effectively realize the projective measurements, because you're not able to do a intermediate measurement on a quantum computer without destroy the whole thing. Okay, so it is in essence a Bradbury process. And then we choose to look at the final output state, because the final output state encodes the full information of the problem. And if you choose to use a certain measure, like the OTOC or the complexity, they can only detect certain aspects, but not all of them. Okay? And what we found is that the final output state always contains part of the information of the initial state. Actually, it's a mixture of the input state and the identity operator. Okay, even though the intermediate projective measurements totally destroyed all the information on Alex qubit, part of the information of the initial information still comes back in the end. Okay, so in this sense, it is exactly the opposite of the butterfly effect. So that's why we call it the anti-butterfly. Okay, I'd like to emphasize something here. This equation, this result, is not the result for a single given unitary. Of course, because for a given fixed unitary, the output state would depend on that unitary in a very complicated form. And if the unitary is chaotic, it's not very likely that you can solve it. This equation actually is the average output state, averaged with all possible unitaries, all random unitaries, with respect to the Haar measure. And the Haar measure actually means that that's the most random case. Okay. And moreover, what we have shown is that the fluctuation in this process, in this average process, is actually very small. It is exponentially small. Exponential in the system size is the number of qubits. So that means this equation is actually very typical for a single given target unitary. Okay, for any target, for any typical chosen unitary, the final output state is actually very close to this form. The deviation is actually suppressed exponentially in the system size. So we're good to claim that this is the actual output state, even for a single given unitary. To test our theory, we studied a more. Yeah.
Before you move on, there's a question also relating to the previous part of your talk. Is that can you characterize the early time regime, and is that the Ehrenfest time?
Yeah, exactly. That yeah, the early time is actually the Ehrenfest time, where you have the correspondence between classical and quantum dynamics. Exactly.
Okay. Thanks.
Yeah. I can. There's another point I'd like to emphasize, that beyond the Ehrenfest time, the quantum complexity distance between those two wave functions is conjectured to grow linearly in time. This is the conjecture and has been proven under some assumptions. Yeah.
Okay, thanks.
Yeah. Yeah, back to this point, the fundamental reason behind the recovery of the initial part of the initial information is not because that the dynamics is linear, because linearity of the dynamics at best tells us that small perturbations remain small, right? It does not accumulate to a huge difference, but it doesn't tell us that perturbation can be recovered, perturbation can be healed, right? So the fundamental reason behind this is because of complexity in the evolution. So Alex local information passing through the complex evolution would be transferred to a global, would be transformed into a global form in terms of entanglement in the rest of the system. So if you apply a local perturbation, that doesn't matter too much. The information is still encoded in the total system, and that can be converted back to the target qubit in the end. to test our theory, we started a more realistic physical model, the spin bus model. We have a single central spin, the big gas, randomly interacting with a spin bus. So on the top figures, this is the density plot showing how much information it transfers back to the central qubit in the end. And T1, T2 of the time evolution, the time for the forward and backward evolution. And you can see that when T1 equals T2, when the evolution is perfectly reversed, you get that part of the information, you always get part of the information recovered for the central spin, no matter how long it takes. The right-hand side is not relevant, not quite relevant here. It's just another technical point in our paper. The bottom figure, however, is the same simulation. It's a simulation for the same process, but for a classical Hamiltonian, the analog to the spin bus model. So we treat all the spins classically, and they also interact classically. And you can say this is the time evolution for the average of the Z spin component. We start from a perfect aligned spin, which is 1. And then at time t, we just reverse the evolution. The green curve corresponds to the case where we do not apply to perturbation at all. If there's no perturbation, of course, everything would be reversed perfectly back to the initial state. While the black dashed curve corresponds to the situation where we apply this intermediate measurement that destroy all the information. And you can say, even though the evolution is reversed, there's no information coming back to the central spin at all, in sharp contrast to the quantum case. So that means that the effect is purely quantum. There's no such effect in classical physics.
Can I ask a quick question? Does
Sure.
it matter here that the model effectively has like?
Sorry, I'm not getting your question.
I hadn't formulated it yet. Does it matter here that effectively all the spins interact rather than just having a local interaction? Or is it a local interaction that's hidden in the definition of the JI alphas?
Yeah, in our case, it's all to all, not all to all. So the central spin interacts with all other bus spins randomly, but there's no interaction between the bus spins. And because the interaction is random, we wanted to have a chaotic dynamics to make it happen.
Okay, thanks.
Yeah, of course we can apply more complex interaction. We should get the same result. The final result should not be very sensitive to the form of the Hamiltonian, as long as it's complex enough.
Okay.
Yeah, and we also tested our theory experimentally on a IBM quantum computer. We use a 5-qubit quantum chips. That's very simple, but we have to carefully design the unitary to make it complex enough. We call it Squamish unitary in the sense that this unitary, for any given state of Alex qubit, passing through this unitary, Alex qubit would become a maximum mixed state. There would be no information here. So in this sense, this is Squamish. Yeah, and as you can see that we get very high fidelity for the output state that confirms our theoretical prediction.
There are 2 more questions from the chat. So first of all, does this anti-butterfly constitute a safe quantum communication protocol?
Sorry, I hear a noise, and so I didn't get your question. Can you repeat, Peter?
Does this anti-butterfly constitute a safe quantum communication protocol?
Yeah. So that's one possible application. I'd like to mention, so people can take this effect and design protocols to securely hide quantum information, because this effect makes information more robust against perturbation. Yeah, sure. That's one possible application. And another possible application is that because this anti-butterfly effect is purely quantum, we can use it to benchmark a quantum computer.
Cool. Then there's a second question asking, for this spin Bath model, does the effect disappear if we use large S instead of spin 1/2 to gauge if the effect is not quantum or if it is?
I don't think I have a firm question, a firm answer here, but I think the essence is this. So our derivation is the average result for all possible unitaries. And if you randomly pick a random enough unitary, you get the same result. So that if the Hamiltonian is chaotic, as long as it's chaotic, you always get this result. But of course, you can always design a Hamiltonian such that you don't have this effect. But that means your Hamiltonian is not typical at all.
Okay, thanks.
Can I ask one more, since we are on the subject? So, to what degree these results depend on the fact that you can do U and then U dagger exactly? Because that U is the one that acts on, is it correct? Am I understand correct that U acts on the spin and on the bath?
Right. It's a global U, yeah.
Right. So I guess my question is, you have to U and then reverse it perfectly.
Right. Exactly. Yeah.
Have you looked at what happens if that's something you cannot do? As one perhaps might think, when you think about the Loschmidt echo, is that you can do a global unitary, or you can try to do a global unitary, but trying to reverse it exactly might be complicated.
Yeah, exactly. That's a very good question. So first of all, I'd like to emphasize that this U is indeed a global U, and on a very large system involving all other qubits. And the larger the system is, the better this equation described the final state, because the fluctuation is suppressed in the system size. And also, if U dagger is not precisely U, of course, you don't get everything reversed. And I would guess that this result, the final recovery of the information would be decaying, just like the Loschmidt echo.
Right.
Yeah.
Thank you. You can go on.
Okay, actually, I'm in the end of the talk, so that's all I'd like to share. And I hope you can take away at least one type of butterflies. And I'm looking forward for more applications of the developed framework and the discovered effect. And I hope there will be more type of butterflies, quantum butterfly discovered in the future. I'd like to acknowledge support from the Center for Nonlinear Studies and DOE Office of Science, and also my collaborators, Nikolai Snessen and Wojciech Zurich. They are also my postdoc mentors, and Łukasz Szyncył from Leno, and also Wissam Kamisoni from Caltech. Thanks for your attention.
Okay, thanks a lot, Ben, for this really interesting talk. Clearly, the audience was also interested. So again, we encourage people to ask questions if they have any left. And I actually have one small additional question, which I was first waiting to ask. So in this spin-Bath model, it's integrable if you choose interactions to be isotropic. So if Ji alpha does not depend on alpha, did you check what happens to the anti-butterfly in that case?
Not yet. No, not really. We haven't checked the integral model for this case.
Okay, I'm just curious.
So I have one that I had actually from the first part of the talk, which was, so when you were analyzing the circuit complexity, you said that you were kind of interested in the classical limit. And if I understand correctly, there is a big part of this that depends on the choice of the M, the set M,
sure.
Right? And you said you chose the Heisenberg group. So is it, could you choose, for example, like Gaussian operations or something like that in the case of when you have a phase space, instead of taking your perturbation to displacements to be something like rotations and squeezing in the case of quantum dynamics. Do you know if that would change anything, or maybe that's not what you care about in the classical limit?
Well, talking about the classical limit, I don't know. My guess is that it might not be very sensitive to the choice because the structure was there. Just like the problem is not sensitive to the choice of metric in phase space, we always get this type of divergence. So I would guess we can, of course, use other type of operators. The reason that we restricted ourselves with Hessian algebra is because it has a natural correspondence to the classical canonical variables. That's much easier to deal with.
Thank you.
There's one more question from the chat. Can you consider more than 2 parties for the anti-butterfly protocol?
Well, I don't know. We can be more specific about more parties. So we're talking about 2 Alex with 2 input states.
I don't know.
Or
if we give it a minute, there might be an answer in the chat.
Yeah, there's a 1 minute delay.
Yeah. You can. Yeah. In the meanwhile, there's another question. Well, maybe this one gets clarified. Does the quantum chaos resulting as a result of quantum trajectories made from a bunch of weak measurements classify into any of these? Just asking because this person could not see the connection. So can you relate this to quantum chaos resulting from weak measurements as a result of quantum trajectories arising from a bunch of weak measurements?
Yeah, I'm thinking about that. Well, yeah, if you do weak measurement, you get a trajectory for the evolution. But that's all I can think of now. Once you get to the trajectory, of course, you can do many things for that. Maybe you can apply this framework to compute the distance between 2 possible trajectories. I'm not seeing a more deeper connection to that.
Sure, thanks.
For the moment, yeah.
No problem. I don't think there are any more questions, and the chat doesn't seem to be active anymore.
Do we get the clarified answer question from the previous question? Okay.
So I think in this case, we can conclude this week's seminar. Thanks again to Ben for giving this really interesting talk. Thanks again to everyone watching. And we'll be back next week at the same time, this time. And if you want to get updates, please subscribe to this YouTube channel or subscribe to our mailing list as given in the description of this video.